Hello again, and welcome to the next chapter about rotations. Now, let's see how to compute rotations. Do not forget, the last things we mentioned is there are two ways to represent rotations. We have a plane, and we can represent the rotations on this plane. And this plane can have any attitude in the space. The other way is, if you have the plane, we can find an orthogonal vector to this plane, and then we can rotate around this vector. Okay, and then if we have a three-dimensional world, then we have measurements in three axes, x, y, and z. We can represent the world transformation as a sequence of rotations in each of these axes. But I hope you remember, we have a problem because rotations are not permutative. Then it's a difference if we compute first the rotation on x, then y and z, or if we compute first z of y and then x. In any case, we are accumulating an error. But there is a standard, and this standard says we begin with the accumulation of the rotation in z, then y, and then x. But do not forget, it's not perfect. We are accumulating errors. We have to synchronize or calibrate our attitude with something else. Okay, then we have micro rotations. If we don't want to accumulate a very big error, then we have to do the integration of the rotations in very small steps, maybe 1,000 times per second. And then we can integrate all these micro rotations to get the total rotation of the system. Typical numbers are from 100 to 1,000 times per second. If the system is moving very slow, that is the case in satellites. Satellites are moving really slow, then we can have maybe a samples rate of maybe 20 samples per second. But if we are moving fast, for example an aeroplane, then we have at least 100 times per second, and if we are moving faster, robots, quadrocopters or something like this, then we shall have a very high rate, as high as possible. 1,000 times per second is a very good rate to integrate the rotations. Okay, now how do we come from micro rotations to attitude? Do not forget, please, we are talking about three different things. dx dt, that is the speed. This is the rotation speed. Then we have delta x. This will be the delta rotation. So we were here and now we are here. So what was the change? And then the attitude. Then what we have to go is from speed to delta and then increment the attitude. We have these steps. First, we have to calibrate our measurement system. An example in aeroplanes, when the aeroplane is started, then it shall stay without movement for about 10 minutes. In that 10 minutes, the instruments will be calibrated. And after those 10 minutes, then the passengers can come to the aeroplane and then we will have vibrations. But before the passengers come, we have to calibrate the sensors. This is something we have to do always. So if quadrocopter or satellite or whenever we have, we keep it without movement and then we calibrate. With satellite is something more difficult because we don't have this situation keep without movement. At the beginning, it's rotating in any direction. Okay, next we have a loop, a time loop. This can be from 100 to 1 kilohertz, from 100 hertz to 1 kilohertz. Or, I said before, for satellite it can be maybe 20 hertz. Okay, the smaller the step is, and the smaller will be the accumulated error. The next step is to read the gyroscope. The gyroscope tells us the rotation rates in all these three axes. Then we convert these rotation rates times the time step, a function of this, and then we get the delta attitude in each of these axes. Then we have to combine all these three axes to one what we call rotor. Okay, we go from here, and this rotor can be represented as a matrix, a quaternion, rotations axis, or something like this. There is a difference here. We have the delta in each axis. But that's not enough. This is, it's okay for a representation, but not for integration. This is in the Euler Angles, only for representation and for measurements. Okay, when we have computed the rotor, we are going to see how to represent the rotors. Then the new attitude will be the old attitude. Remember, we write from right to left. Okay, the old attitude multiplied by the new rotor. And this multiplication is a matrix multiplication or quaternion multiplications, or the multiplication according to the encoding of the rotor, which can be different. And of course, the attitude shall be encoded in the same way like the rotor, matrix or quaternion. Okay, now we have 2 or 3 alternatives for this computation. This computation here, attitude equals rotor times attitude, the old attitude. Okay. First, do you remember we have 3 measurements? Then we compute the total rotor. And the total rotor will be the multiplication of first z, then the rotor on y, and then the rotor of x. Then the new attitude will be the old attitude multiplied by the total rotor, which is composed by these 3 rotations in 3 axes. Or we can do it step by step. The new attitude will be the old attitude multiplied by the rotor in z. Then the new computed multiplied by the rotor in y, and again the new computed multiplied by the rotor in x. Or we can do a multiplication of all 3 rotors. Then we have this rotor z, y, and x. When they are multiplied, we get a rotor which includes all these rotations, and then we multiply the attitude times the new rotor, and then we get the attitude. And you will ask, what is better? The result is the same. Maybe you will get the impression this will be better because we are accumulating the attitude in each step directly without first creating the total rotor. But the result is exactly the same, makes no difference. And now, what is a rotor? We are going to see 2 main ways to make a rotor. First, the matrix, then quaternions, and here what I say, the Euler Angle, roll, pitch, and yaw, where we measure the deviation in each angle axis. And what I said before, this is only for the output to show it to the pilot or for the measurement. But for computations, I really do not recommend this. This works only for very small deviations. For big deviations, you are going to accumulate a terrible error. So we are going to handle only matrix and quaternions for computations. Okay, now we have another small step. Do you remember? Here we are computing the rotor, here. We are computing the rotor as function of the measurement of the rotations. And maybe you think we are assuming this is the rotation of the body, how the satellite or how the car or aeroplane is rotating. But this is not the rotation of the body, this is the rotation of the rotation measurement unit, the IMU, for example this. Then we have one more step. In every IMU, we have these coordinate systems. So we can see in which direction is x, y, and z. And of course, when we measure the rotation, we measure relative to this axis of the IMU. And then we have to convert the mounting frame of this IMU to the car, aeroplane, or satellite. One more step. We have to represent this mounting frame from here to here like a rotor. It's the best way, so we can do everything with the same type of rotors, matrix, or quaternions. So the IMU attitude will be what we said before, the old attitude of the IMU multiplied by the rotor, which we measure from the IMU. But we don't want the attitude of the IMU, we want the attitude of our device. Then a small one step, then we multiply the IMU attitude, what we compute here, times the mounting arrangement of the IMU. And then we get the attitude of our satellite or car or aeroplane. And where does this come from? This comes from the constructor of the device. He knows how he mounted the device, and then he will give us this transformation matrix or quaternion or whenever we want. The other way is to make own measurements, because this mounting arrangement is what they made in the design, but when mounting, the real mounting, depending on the force in each of these screws, the device is going to rotate a little bit in any direction, or maybe after vibrations, it will move again. So what the computation of the design are not exactly what we need. The best way is to make measurements and then compute this rotor from the mounting frame from the IMU to our device. Okay. And now, where shall be the IMU be mounted? Maybe you will get the impression it shall be in the center of gravity, or it shall mounted in the axis of rotations. But actually, it makes no difference. It can be mounted anywhere in the device. For example, one rotation here, 360 degrees, is the same if we are exactly in this axis or we are outside of this rotation axis. The 360 degree will be the same. So do not take care about this, do not worry. We can mount the IMU anywhere in the device. By the way, this is exactly the same case when we are talking about the reactions wheels to control the rotation of the satellite. Maybe you will think it shall be in the center of gravity, but makes no difference. It can be anywhere in the satellite. Okay. Now, all this was inertial. Do you remember the different coordinate systems we have? And we say there is one very special, which is the inertial coordinate systems. And the IMU is measuring the rotation speed in the inertial coordinate system. But now we would like to make a transformation to another system. For example, if we are on the Earth, we would like to know our attitude relative to the Earth. Or do you remember the navigation frame, which is here? Or maybe in orbit, and okay, we saw so many frames in orbit, so one of them. Then we need another rotor. And this rotor will be the transformation of the attitude of our satellite to the attitude of here, of the Earth or navigation frame or inside of lab. It doesn't matter. So we need one more step to multiply by another rotor. So we have one rotor which defines the translation, the rotation from inertial to XX. XX is anything else. Okay. Then at the beginning we have our old attitude, inertial, and then we multiply by this transformation from inertial to XX, and then we have our attitude relative to XX whenever you want to be XX. Okay. Now something about mounting frames and the arrangement of the device, of the measurement unit. Just a second. And now let's talk about this line, only this line, how to define the rotor. We are going to see two different ways to define the rotor, using rotation matrix and using quaternions. These are the most common used and the most important. So then let's begin with the matrix. Maybe do you remember we were talking about this a few hours ago. Okay, we define this is a point, and this point has fixed coordinates relative to this coordinate system. Let's say this is the body coordinate system. It's attached to the body of the satellite or aeroplane or whenever you want. And this is, for example, where the camera is pointing to. Then you have your satellite and the camera is pointing in one direction. If you rotate the satellite, the relative position of the camera to the satellite will be always the same, but the relative position of the camera changes together with the attitude of the satellite. This is the position relative to the Earth, to the sun, or what you are looking at. Let's take this example. Maybe you remember in a two-dimensional world. We are going to begin with a two-dimensional world, and then we are going to go to 3 dimensions. A point or a vector has only 2 coordinates, this and this, for example, and they are relative to these 2 vectors. We are going to define the x vector as 1, 0, and the y vector like 0, 1. And this is the origin, 0, 0. Okay. Then the position of this vector is this x of the vector multiplied by the vector x. And then the y component multiplied by the vector y. This. Then we have 0.8, times this vector 1, 0 plus 1.4, the second element, multiplied by this vector 0, 1. The result will be 0, 1, 0, 0, 1, 4. If we add, we get 0.8, 1.4. And if you see, it's exactly the same. Then you are wondering, why shall we do all this to get exactly the same? Now we are going to see why. These vectors are not going to stay the same. Now we are going to rotate the body. After the rotation of the body, these two vectors have another coordinates relative to the reference coordinate system. That is my reference coordinate system. The original x is still 1, 0, but the rotated x, let's say we rotate with an angle on alpha. Then we have other coordinates for x and for y. And this is my new reference, my new body coordinate system. And the vector or the point here will rotate together with my device. So let's see. This was the original point or the original vector. Now we have other coordinates. And these coordinates are still the same relative to these vectors, but not the same relative to the reference coordinate system. Okay, the operations which we define are the same. I don't know now the new position of this vector, but I have to do the same. Plus, first I have to find the new coordinates of this vector, First, without any mathematics, just by looking. If we take a look, I will say this position here is about 0.95. And this position here is about 0.35. So I will say that is the new vector x. And something similar like the vector y. If I take a look here, I will see that is minus 0.35. And in the height it is plus 0.95. Okay, this is the new vector y. Then, if I multiply this original point vector times this and add times this, then I shall get the new position relative to the reference coordinate system. Let's see, I don't know the new position, but I can make this multiplication. The x coordinate times the new x vector, and exactly the same with the y vector. Okay, this will be this multiplication. Look at this. This is the x vector, and this is the y vector. You can see. Okay, then the new point will be 0.8 times this and times this, plus 1.4, the second element, times this vector, this and this. Okay, then the result, if I add these two things, will be this. You can follow. And if I add this term with this term, I get 0.27. And if I add this term with this term, I get 1.6. And this is, if we take a look to the new coordinates relative to this reference coordinate system, we will see, I think it's right. We are at the right position. Okay, so we can make a rotation by alpha in a two-dimensional plane. But now, let's use some mathematics and not only guessing these numbers. Okay, how to do that? Let's use sinus and cosinus. I hope you remember the definition of sinus and cosinus. If we have a vector with length 1, then at any point, this point will have the coordinates cosinus alpha, this is the angle alpha, and sino alpha. Okay, the position xy will have a length of 1, and then the position is cosino alpha, comma, sino alpha. This will be the position. Okay, and then let's do this here. This position here will be, as expected, cosinus, sinus. And the other direction, we rotate everything together without the formation of our satellite by alpha. And this new position is plus 90 degrees, because from here to here we have 90 degrees. Then we can look in our mathematics book what is sinus from alpha plus 90 and cosinus from alpha plus 90. This is what we have here. And your mathematics book, we find something like this. Cosinus from alpha plus 19 is sinus minus sinus from alpha. And you can see it's a negative value. It's right. And cosinus is sinus. Cosinus from 90 plus alpha is sinus from alpha. And why sinus becomes cosinus is because sinus and cosinus are shifted by 90 degrees. It's clear, huh? Then that's it, the coordinates from my new y vector. Minus sinus from alpha, cosinus from alpha. Okay, then I have my new two vectors. Then I have this point. And I want to find what is my new position. And I know with using some mathematics, the new vectors, my body system. Okay, just to remember, we can do the same here using the complex plane. Then this is the imaginary vector and this is the real vector. Then this point will have these coordinates, cosinus. Oh, sorry, here you shall see cosinus. Oh, this is cosinus, yes. This is cosinus from alpha in the real value plus sinus from alpha times imaginary. Okay, why shall we do that? We don't need it now, but later when we are dealing with quaternions, we will use it. So remember a few minutes later why we are using the complex plane. Okay, but at the moment we don't need this. We are going to get this definition. Okay, now we see how to rotate a point. The original was xy, two scalars, and this is the new x and the new y vector. Okay, the new point will be the x component times the x vector plus the y component times the y vector. Okay, this is the x vector as you can see, and this is the y vector as you can see here. And this is the multiplication we said before. Okay, the new xy will be this vector and this vector multiplied by the old point. And this will be my new point. So I'm building a matrix using these two vectors. Okay, and then I define my rotor will be this matrix. And this matrix is the new position of my body coordinate frame. So, as you can see, this is my new position. And the new point is the multiplication of the old point times the rotor for this angle alpha. Okay, and we did it. So, we are going to deal with rotations, and this is our rotations matrix, or we can say this is our attitude. So, I can say that this matrix defines the new attitude of my satellite or an aeroplane, in this case only in 2 dimensions. The next step is going to 3 dimensions. How shall we do that? In a very similar way. Okay, this is in 2 dimensions. We have to add 1 dimension. Let's do exactly the same. The new x is where the all 1, 0, 0 strikes after rotation. Exactly the same with y and exactly the same with z. The old z was 0, 0, 1. And now I have to see where it will be after the rotation. And this is my body coordinates frame. And the rest will be exactly the same like in 2 dimensions. Okay, then I have my point is P1, P2 with 3 scalars. My new point will be this, again with 3 scalars. And this is my new x vector, my new y vector, and my new z vectors. I am using the colors not for this vector, but to the reference coordinate frame. So my new x body frame will have this coordinate x in the reference coordinate frame, and x2 in the reference, and x3 in the reference. So let's say these are the 3 elements. We could say x, y, and z. Okay. Now let's see how to proceed. Exactly the same. The new point had 3 elements, is the multiplication of the first element times the x vector plus the same with y and the same plus Z vector. Then I take these three vectors together and I build a matrix exactly the same in the same way like I did before. This is my matrix. Okay. Then I want to show that this matrix here is my new rotor in 3 dimensions, and this is exactly the same like this multiplication. So I don't want to write this very big term. I want to write a little bit shorter. Then I'm going to use matrix and use matrix multiplication, matrix with matrix, and matrix with the vectors. Else I shall write a lot of terms, which is really difficult and error prone. Okay, so the new rotation matrix or transformation matrix will be this vector, which consists of these new positions of the body frames multiplied by the old positions, and this will give me my new position. Let's show it works. Do you remember how to multiply a matrix with a vector? We multiply these two plus this plus this plus this plus this, and this will give me the first position of my new vector. And then let's see, then I have xy times p1 plus y1 times p2 plus z1 times p3. And now let's take a look to the main first definition, and you will see it's exactly the same. So I have a shortcut. I don't need to write so many terms. I can say define only this is my rotor, and then multiply my rotor times the point, like I said before. This is my rotation matrix or my rotor, and I multiply this point. So else I will have to write a lot of things which I don't want. Okay, as a few remarks which will be interesting. All these three, the original x, y, and z, and after rotation, they have sharp the length of 1. If we change this length, then we're stretching or satellite or aeroplane or whenever you are having, and we don't want to stretch it. It's a fixed structure. Another important thing is they shall be orthogonal. If not, we are squeezing or changing the shape of our device. So these two things have to be held always. A length from 1 and orthogonal. Okay, let's continue with 3 dimensions. Okay, I said before this was the rotation in 1 dimension, and I have to add 1 dimension. Do you remember? I am adding here the vector z. And with that point, this means this vector is looking from the paper to you or from the screen to you. And if you take your right hand, you will see this is a right-handed system. So the z vector shall point to you. If we have a cross here instead of a point, then the z vector will look from you to the paper or to the screen. And then try to match it with your right hand, you will see it is not possible. So it shall be in the other direction. The z vector should lie to you. Okay. And now let's make the next step, how to compute rotations in 3 dimensions. First, do you remember this? We are going to use this again and again. And I am rotating here, only on the xy plane. So this was my old x, and this is my new x. That was my old y, and this is my new y, and I am rotating by alpha. Okay, this was my old point, and my new point is here, relative to the reference coordinate system. Relative to the body coordinate system, it didn't change. And now try to see how does the z coordinate change after these rotations. And you will see they are still in the same plane. So the z coordinate didn't change. Okay, what do I have? My rotor is defined like before with these 3 vectors, each vector with 3 components. And then x vector from here to here is cosinus sinus, and I don't know the third value. But I can see from here it didn't change it didn't rise, and it was not lowered. After these rotations, it stays still in the 0 position of z. So this shall be 0. So my new x is then cosinus, sinus, and 0. So in z, it has no component, else it will not be orthogonal to z. Something similar with y. Those are the new coordinates of my y vector, and relative to z is still 0. And what can I say about z? This was the original z, and this is the new z, and you can see they are the same. And the original z was 0, 0, 1. Do you remember? So z didn't change. It's 0, 0, 1. Okay, and then I can say this was my rotor if I rotate on z with the angle of alpha. Okay, then if I combine these three vectors, my new rotor or rotations matrix will be this cosinus sinus 0 minus sinus cosinus 0, 0, 0, 1. And this is the rotor rotating around z. So I define the rotor of z with the angle alpha, define these three new vectors, and correspond to this matrix which we saw before. Okay, and something important then, the new point P will be the old P multiplied by this rotor, which was defined here. Okay, and now let's write it again. This is the rotor Z alpha, and this is the rotation, and this will be the new definition of the point. This was only for Z. And now let's try to do exactly the same for the other three axes. Okay, just to remember, this was the rotor from Z, and if we do the same for the rotor for X, we expect something very similar. The X vector shall not change, it shall stay 0, 0, 1, and the other vector shall have a similar transformation like this. Okay, and it will be the rotor of X by phi shall have, in X didn't change, the X vector is still the same, and this transformation is still here, the same from here to here. So you see, we can do exactly the same. Well, we can make all drawings again to show it's right, but you can believe me. With X, with Y, it's a little bit difficult. Then the Y vector is the same, 0, 0, 0, 1, 0. The Y vector didn't change. And the Y component from these two other vectors didn't change. But here we see there is an anomaly. This sinus is now minus sinus, and this minus sinus is now sinus. So we cannot just shift this and make these two lines in the center. We have to make a transposition or inversion of this. Okay, just remember, there is a very complex explanation why is it so, but we are not going to show this explanation now. Just remember, when you are creating the rotor on Y, you have to invert both sinuses. Okay, and now let's take a chain of rotations. In the example before, we rotated only of Z, for example here, or only in Y, or only in X. But now we have all these three rotations and we have to combine in a single rotation. Or a little bit more complex example, going from here to here, we have to go a long chain of translations and rotations. So we have to concatenate several rotations. Let's see how to do that. Okay, we have our rotations matrix. This will be my new rotations matrix. And just to remember, these are the three rotors I explained before. Okay, something important. When we are going to create a concatenation of rotations by multiplications of rotors, multiplications of matrices in this case. Something very important, they are not commutative, like matrix multiplication. So when we are multiplying two matrices, you cannot interchange the sequence. In matrix multiplication using normal mathematics, it will not be the same. And it is exactly the same with rotations. If you rotate first in A and then at B, is something different than rotating first in B and then in A. So keep this in mind. But if we have a sequence of X, Y, and Z, all they were measured at the same time, but to make the operations, we have to make a sequence. Well, we are going to make a small mistake. I said this already several times. So we are going to multiply to rotate first Z, then Y, and then X, even if we are accumulating a small error. But this, I said this already many times. Okay, now let's make an example. Assume we rotate in Z by phi, and then in X by alpha, and then again in Z by beta. we could say, okay, we are rotating this and this, both are in Z, so we could add both values. But it is not true, because before I rotate this, I make a rotations in X, and when I am rotating in X, I am changing the Z axis. I'm going to show you. For example, here, this is Y. This is my original X, Z, and if I rotate this, you can see I will move Z in this direction. Let me show you. Okay. Here I have it again. This is the rotation in Z. Let's say I rotate one angle and one angle again. So I could add both angles. But if I in between I rotate other axis, then I'm changing Z. For example, I rotate here an angle, then I'm rotating here. And look, the new Z is something different. Then I'm rotating again in Z, but it was not the same vector like before, because in between I had another rotation and I changed this rotation vector. So I cannot add this. I have to multiply the rotors. Okay, coming back. And I said, when we are concatenating rotations, we write from right to left. So first I rotate Z on phi, then I have this rotor. Then I rotate X by alpha, then I have this rotor, and then I rotate Z by beta, and then I have this rotor. And then I have this multiplication of these three matrices. In this case, the rotors are matrices. And these are the matrices which I am using. Okay. There is something I shall say. I am always saying, okay, the first rotation is right and the last rotation is left. This is in the case what we are doing with the aerospace control, because we are moving and the rest of the universe is our reference. Others do something different, for example, games and computer graphics or something like this. For example, when they are moving the camera, from the point of view of the observer, they are in the same position and the world is rotating. So the world is rotating. Therefore, if you are moving the camera, then you have to use the opposite sequence of rotations. The first come to the left and the last to the right. But this is something important only if you are working with computer graphics and rotating the camera. In our case, we don't have a camera. We are rotating and the rest of the universe is our reference. So, from right to left. Don't forget it. Okay, I shall say something. I said we shall not use Euler Angles for computations. Roll, pitch, yaw, because we're accumulating a big error, so we cannot use at angles. But here, if you take a look, it looks like Euler Angles. I am rotating this angle, then add this rotation and add this rotation. We can do that only for very small deviations, only to convert the measurements to the rotations matrix. But from there, we are going to continue with rotations matrices. Okay, now I would like to say something for going in one direction and then coming back. Of course, you know, if you rotate so much in this direction and then you rotate again in the opposite direction, then the result shall be the same. Let's see how it works. Okay, we have, let's take the example rotating on Z, this Z. Okay, my rotor in Z alpha is this, what you remember. Okay, then I have to define the invert. And the invert is, of course, the same rotor on Z, the same axis, but the inverted angle, minus alpha. That shall be the inversion of this rotor. Then you can write where you have alpha minus alpha. And you will remember cosinus from minus alpha is still cosinus from alpha. It's the same. But sinus from minus alpha is minus sinus from alpha. Then the cosinus will not change. They will stay cosinus from alpha and cosinus from alpha, and the sinuses will be inverted. This minus sinus will be a plus sinus, and that's plus sinus will be a minus sinus. And that is the inverted rotor. So we have two ways to do that. First, just invert all sinuses in the whole matrix. And the second, just transpose the matrix. And the transposition of the matrix works because all these vectors are orthogonal. And the inversion of a matrix, if the vectors are orthogonal, is the same like the transposition of the matrix. So both are the same. Here I have the explanation why. Okay. Now I'm part interesting informations. Let's say I have these three vectors. You remember our rotations matrix consists of the three vectors after the rotation. And these three vectors, I'm going to call them U, U, V, and W. And the rotor from B to K, let's say I have this rotation from this position to this position, is exactly the same like the inverse rotation from K to B. And because they are orthogonal, it's the same like the rotation from K to B, transpose. Okay, and these three vectors, they have to be orthogonal. So if they are orthogonal, the dot product or scalar product of each of them shall be 0. I hope you remember this from mathematics. And the vector product or cross product from any of them shall give the other one. For example, the cross vector product of these two shall provide this. And the vector product of these two shall provide this. And something more, the length of each of them shall be 1. Shall we try? Okay, let's try with the rotor from Z and alpha. Okay, this is U, this is V, and this is W. And you can see the length is 1. Sinus square plus cosinus square plus sinus square, I hope you remember, this is 1. Exactly the same here, minus sinus square plus cosinus square, that is 1. And this is 0 square plus 0 square plus 1 square is 1. So you can see they have the length of 1. And now, are they orthogonal? If they are orthogonal, then the scalar product shall be 0. Let's see. Let's try only the first one. Okay. U scalar product with V. This is cosinus times sinus minus sinus. This is cosinus. Wait a minute. Cosinus times minus sinus plus sinus times cosinus. As you can see, it's inverted. So the sum of these two terms is 0. And then plus 0 times 0. Okay, is 0. So with the first one, it works. You can try by yourself with the second and with the third one. And you will see they are orthogonal. The other interesting thing is when multiplying any of these, you shall get the one which you are missing with the scalar vector product. Okay. At home, if you want, you can try it by yourselves. Make these vector multiplications, and you will see if you multiply U times V, you are going to get W. Okay, you can try it later. Okay, and another thing, do you remember from the last lesson, we were using the direction cosinus matrix. And this was, if I have two coordinate systems, I can multiply scalar products of the three axes of one coordinate system with the three axes of the other coordinate system, and then I'm going to get a matrix, which it will be my rotor from one coordinate system to the other coordinate system. So, for example, if I am moving from here to here, and I want to have the rotor from this, then it's the cosinus direction matrix of this. And do you remember? Let's say that was x was before the rotation, and x apostrophe were after the rotation. Exactly the same with y and with z. And this is the definition of the cosinus direction matrix. You can look at the other movie to check. Okay. And you remember the multiplication. Wait a minute. Yes. The multiplication of a vector with itself, I mean the scalar product of a vector with itself is 1. And the scalar product of the multiplication of two orthogonal vectors is 0. Okay, then we are going to try. Let's assume we have rotated by alpha only on z. So x times x will be the cosinus of alpha. Do you remember? If you multiply two vectors, then times using the scalar product, the multiplication is the cosinus. So this will be the cosinus. Correct. And these two vectors, it will be the cosinus from alpha again, the sinus, because I am changing the plus 90 degrees. Do you remember? Okay. And in this case, these two vectors, x and z, take a look, they are orthogonal. So the multiplication shall be 0. And in this case, z times z after the rotation, z didn't change, is still the same. And you can see, if you multiply a vector times itself, the result shall be 1. Okay, then it shall be 1. So you can check this cosinus matrix, if you are rotating, and z will produce this matrix. And I hope you remember, this matrix is the rotor of z. Let's go a few slices back. Here you can see, this is the rotor of z. So it is right, it works. So we can get the same result if we use this method which I showed you before, or if we use the direction cosinus matrix. And now let's go to concatenation. I said before, it's only the multiplication of different rotors. Okay, let's assume matrix multiplication, and its rotor in this case is a matrix. I have this first transformation, this rotation, and then this rotation, and then the new rotor, which includes both rotations, is the multiplication of these two matrices. The result will be this times this, plus this times this, plus this times this, and this will be the first point. And you can do exactly the same for root points. Okay, we are not going to repeat this. I hope you remember this from your algebra lectures. So this will be the new matrix, which is the multiplication of these two matrices. And now let's try, this is what I said before, with this rotor. I rotate x on alpha, y on beta, and z on phi. And this is, and I'm going to use this role with Joe. So first I make the multiplication of z times rotor on y times rotor on x. And do you remember these three matrices? If you multiply these three matrices, then you are going to get this. You can try it by yourself if you want. It's a lot of work. Okay, and this here is the new rotor, which includes these three rotations on these three axes. Okay. Next point. Concatenation in one direction and coming back. Do you remember? Let's say I have these three rotors, or let's say I have rotor A, rotor B, rotor C, and the result shall be the rotor D. Okay. If I want to compute the rotor D, I hope you remember what shall I write here. I shall write in this direction A times B times C. And when I'm going back, I'm going to use the inverse from D. Then I shall go the inverse from A, from B, and from C. Now the question, in which sequence shall I use? If I am going then and then, when coming back, I'm going the same way back. So the sequence is changing. Let's assume I go here, here, and here. That's what my sequence, here, here, and here. When coming back, first this, then this, and then this. So I invert the sequence, and I invert each matrix, or each rotor. So I said before, my total rotor shall be A times C, A come to the right. And when going back, I multiply C inverse times B inverse times A inverse. And this is the way back after these three rotations to come to the same point where I started. Okay. This is concatenation of rotors. And let me see, just a second, please. And here, if you want to make some mathematical exercises, you can try if this rotor on set, if you add two angles rotating in the same axis, for example, rotating on set, first this and then this, will be exactly the same as only one rotation with the sum of this angle. If you don't change in between the direction of this axis. And then this will be the rotation on beta, and this will be the rotation on alpha, both on Z. And then you shall multiply this. And the result of this multiplication shall be this. And if you take a look using your math book, you can see what is cosinus from alpha plus beta, and you will see this here is this per definition. And then this corresponds to the cosinus from alpha to beta. But I'm not going to do it now. It's only to show you, so if you want to do the exercise by yourself. Okay. And now how to program rotations. It was only the mathematics, but now let's create a small program for concatenation of rotations. Let's assume I have a vector V. And this vector is, for example, from my star camera or anything which I have attached in my satellite. And then I have the matrix A, which is the rotation. And I have these three rotations, A, B, and C. Each of these is a 3 times 3 matrix. This is 3 different rotors. And then I have two different vectors. V, the original vector, and W, the vector after the rotation. So, for example, if I am rotating by A, the new vector after the rotation will be the multiplication of this vector times the rotation matrix. Okay. And after rotation in A, I rotate in B, then I do the same. W times B will be the new W, and then I rotate on C. Then W times C, then I get the new W. Okay. I could do it in another way. I can first multiply all these three rotations. Remember, first A, then B, then C, going from right to left. And then I create a new rotor. And this rotor includes already these three rotations. And then I just multiply by B, and then I get W. Or I can do it step by step. I multiply these two, the results by this, by B, and the results by C, and then the result will be W. These three ways are exactly the same. Or I can create a new rotor matrix. D will be a new matrix, and this matrix will be the multiplication of A times B times C, and this will be my new rotor, which includes all these multiplications, all these rotations. And then the new vector W will be the original vector V times the total rotor, and this will be W. Okay. And if I am doing like the opposite, working with computer graphics, the camera seems to be at the fixed position and the world is moving around this camera, then I have the opposite sequence. First A, B, and C in the other direction. But be aware, this is not what we are doing. This is another world, another group of people. Okay, the next point will be quaternions. Now let's talk about how to rotate with quaternions. Quaternion is a very nice thing. I prefer quaternions. In difference, like rotations matrix, when we are rotating using matrix, do you remember we find the rotation in X, then in Y, and then in Z. It's like going through the corner. So if you want to go from this point to this point, then you will go like this, then like this, and then like this. That is not normal. Normally you take the direct way, and this is the direct vector. And this is something similar what we are using with the quaternions. We don't rotate first in X, then in Y, and then in Z. We find the direct rotor, the direct rotation axis, and we are going to rotate around this axis. And another important thing, rotating with quaternions is in a three-dimensional plane, imaginary complex plane. Do you remember we were talking about how to rotate on a complex plane using imaginary and real numbers? It works very nice. Use multiplication instead of very complex sinus and cosinus what we have here in rotations matrix. But what we showed before, it was rotated only in one plane. It was a two-dimensional rotations or only one-dimensional rotations axis, one point. Here we have to rotate in a three-dimensional space. Therefore, we need three different imaginary numbers. And this is something very complex, but we are going to show how to use, and then you will see you can work with this. Okay, now let's see the definition of quaternions. We have two different definitions of quaternions because they were invented two times, almost at the same time. Einmal they were invented by a Mr. Rodriguez, and 3 years later it was invented by a Mr. Hamilton. But they were working in different countries, doing different things. Even if the Mr. Hamilton invented it 3 years later, most people are using the Hamilton quaternions. The only difference is the sequence where to write the elements. The rest is the same. The mathematics is the same. So when we are talking about quaternions, we are talking about H or Hamilton quaternions. And this is the definition of a quaternion. This is a Q. Q is a quaternion, is a four-dimensional vector. And the Q consists of two elements. An scalar, which is a real value, and in this scalar we encode the number of degrees or the rotation, how much to rotate. And then we have a vector, a bold Q. And this bold Q, this is a three-dimensional vector, but imaginary vector, using three orthogonal imaginary numbers. And this vector, this encodes my rotations axis, where I am going to rotate, for example, this axis, let me see, this axis, and in Q, I encode how much to rotate. Okay. Oh, here is something I cannot translate. This is because I did these slices in German, and Q in German is Q, and Q is a cow. And this is bold, and in German bold is fat, thick, and I said this is the dicke Q. And this was, okay, I'm word as I cannot use in the translation, sorry, but it's a nice thing if we are talking in German, the dicke Q, this is the dicke Q, the bold Q. Okay, okay, the definition of quaternion is the sum of this scalar plus this vector. And this vector, I said before, is a three-dimensional vector which represents my rotations axis. And then the quaternion is this. Okay, there are a few things we have to define. Normally, we need normalize quaternions. If the quaternion is not normalized, after the rotations we are going to change the length of our vector. So we are stretching of satellite, which shall not be. Therefore, everything we have to be very carefully. All quaternions we are using are normalized. So the length shall be 1. And the length of a quaternion is the sum of the squares of these four elements. And then the root of this, like Kant's normal. Okay, and now the definition of quaternion, as I mentioned before, is this scalar plus three vector. The original from Mr. Hamilton and Mr. Rodriguez is much more complex. So we are using three imaginary numbers. The square of each of these numbers is -1, and if you multiply any two of these, you get the other one. So, like using with orthogonal vectors. If you multiply two orthogonal vectors, you get another orthogonal vector. And this is what these two persons were doing with imaginary planes or complex planes. But this is really, really difficult to understand, very difficult mathematics, which we are not going to use. For us, a quaternion is just this, what I am showing here. Okay. Something very important, we have to initialize a quaternion. Do you remember? We try always to have quaternions with the length of 1. So be very careful, never initialize a quaternion with 0. Because else, if you will try to normalize by 0, you will have a division by 0, and then all your operations will be grown. So never initialize with 0. A 0 rotations will be initialized with 1, 0, 0. So around a vector 0. I'm going to explain this later. I said before, never try to normalize 0. This will cause a computation error. About rotations with imaginary numbers, do you remember in last movie we explained this? If we have our imaginary or complex plane, we have this direction with real numbers and this direction with imaginary numbers. And we can encode any vector as the sum of a real plus an imaginary number. And we can encode any angle from any vector by the position of this point with a length of 1. Okay, but I am not going to repeat this. I'm going to recall you. Remember how to add rotations with complex numbers. And it was only multiplying two complex numbers, you are adding rotations or accumulating rotations. And now, how to multiply something which has a real part and an imaginary part. It's like a binom. Let's assume we have two quaternions, two binoms. The first is real and the second is imaginary. That is for A and B. And then we want to multiply this binom plus times this binom. This, remember, this is real, that is imaginary. Okay, if we multiply, we do it like in school many years ago. E0 times B0, what we have here, plus A0 times B1, what we have here, plus A1 times B0, we have here, plus A1 times B1. This is this. And now, why do we have a minus here? Do you know? Because we're multiplying two imaginary numbers, I and I. So if we multiply I times I, we get minus 1. So therefore we get this minus. And then we have to differentiate. Some of these terms are real numbers and some of them are imaginary numbers. If you take a look, these multiplications, multiplying two real numbers, you get a real number. Multiplying two imaginary numbers, you get a minus a real number. Multiplying a real with an imaginary, you get an imaginary and another imaginary. So this is what we are going to use later. And there is something more. Using quaternions, they will not be only imaginary, they will be vectors. And this will be scalars. In the first part of the quaternion, I would like to recall you, we encode the angle of rotation, and the second part, the vector, we encode the axis of rotations. It's only recalling you. Okay, now we have the real part and the imaginary part of these multiplications. And do you remember what I said before? Multiplication of complex numbers is like integrating rotations or adding rotations. This is what we need. So we are doing everything with multiplications of complex numbers in three-dimensional complex plane. Okay, again, our definition. Do you remember the DQ in German is this? Oh, sorry. Okay, and then how to define this vector and this scalar. Do you remember if I am rotating from here to here, let's say for example from here to here, if I make a vector product of this, I will get my rotations axis. This will be this, for example. And if I make the scalar product of the both multiplications, I will get the cosinus from here to here. And this is what we are going to use now to define the quaternion if I am, for example, rotating this vector from here to here. Let's say my original vector is V and my final vector is W. So the vector product of these two vectors will provide this. And now the scalar product of this both will provide the cosinus of this. Okay, like this. Do you remember? A will be my rotations axis and alpha will be the angle between this and this. Okay, per definition, this will be the rotation angle, but this will be the cosinus of half the angle. From this multiplication with the, where is it? Sorry. Okay, the scalar product of these two vectors, I will get the cosinus of alpha, but I need the cosinus of half alpha. do not make a mistake. It will be a mistake to say, okay, then I make the scalar product of these two and I divide by 2. It is not. It is not half cosinus. It is the cosinus of half alpha. So I have to increase the complexity. This function will be first the multiplication of these two gives me the cosinus. Then I apply the arcos cosinus. Then I get the angle. Then I divide by 2. And then I apply cosinus again. A little bit complex and not nice, but this is what we are going to have here. It could be so nice if we have used alpha. Then it's only the scalar product. But why shall we use half alpha? The reason is cosinus is ambiguous. If we are rotating from 0 to 300 degrees, 360 degrees, then every value of the cosinus will have two possible values of angle. For example, if we take this value of the cosinus, almost 0.5, then the corresponding angle will be almost 50 degrees or almost 300 degrees. So you see, they are both. And this will be bad. We don't want ambiguous rotations. We want to do unambiguous rotations. The solution is we take only half of this. So from 0 to 180 until here, it's unambiguous. So if we divide the rotations by 2, then we are going to have an unambiguous cosinus. Well, and what if we are rotating by 360 degrees? Okay, it's not a problem, it will be ambiguous, but if you are rotating 360 degrees, at the end you will have the same from the start position, so it doesn't matter. You can rotate as you want, the result will be the same. Okay. And now, how to get this? This is, I said before, the cosinus, the definition will be the cosinus of half alpha, which is a little bit more complex than use the cosinus of alpha. And now I require a quaternion to have a length of 1, to be normalized. I have two elements. The first one is cosinus from half alpha, and the second one is the rotations vector normalized. Here I am normalizing my rotation vector. But I shall multiply this by anything, by something. And this something shall provide me an normalized vector. What shall I be? The solution is I can multiply by sinus. This scaling these vectors doesn't change the direction of the vector. It's making only shorter and bigger, but the axis is going to be the same if it is shorter or bigger. But important is, if I multiply that by sinus, then the quaternion will be normalized. It will have a length of 1. Okay, that is what I have to do here. This is the quaternion, the scalar part, the cosinus of half angle, and the rotation, the normalized rotation angle times sinus of this. So, do you remember sinus square plus cosinus square is 1. So, the length of this will be 1 because the length of this is 1, 2. Okay, and that is the reason why we have here the sinus. Nothing else, just to have a normalized vector. That's all. Okay, so the total quaternion will be the cosinus of half alpha and the rotation axis multiplied by sinus from half alpha. And then, okay. And if we have two vectors, I'm going from V to W. Let's repeat how to build the quaternion. The Q0 will be what we said before, the scalar product of these two vectors, the arcos cosinus divided by 2, and then I make the cosinus of this. And this will be the cosinus of half alpha. Okay, and the rotation vector will be the cross product or the vector product of these two vectors from here to here. Normalize, divide by this length, and then multiply again by sinus of this. This is the same. Look, this is exactly the same. Nor here I am having cosinus, and here I'm having sinus. And that is the definition of quaternion. And now how to rotate using quaternions. This is a little bit more complex. We have to define a multiplication operator. And this multiplication operator works for four-dimensional vectors. You know, until now, we have the three-dimensional vector product, but it works only for three-dimensional vectors, we have to define a new way to multiply for four-dimensional vectors. And this is this circle with the point in the center. It looks like a vector looking to you, so you can remember what is it. Okay, and now I'm going to rotate. This is a quaternion, my rotation quaternion, and I'm going to use an operator to multiply four-dimensional vectors, and I have now a small problem. This vector, which I would like to rotate, it's not a four-dimensional, it is only a three-dimensional vector. So I'm missing something, and I have to convert first this vector to a four-dimensional vectors in order to multiply this by this. Okay, we define the multiplication or the rotation of one vector like this. Going from here to here, we compute the rotation quaternion, and this is the invert of this quaternion. So with this quaternion, we go from V to W, and with the inverse quaternion, we go from W to V. Why it has to be like this? It's very complex mathematics. We are going just to take it as is. We know it works, so we are going to use this as is. So the rotation will be the multiplication of the inverse vector times the original vector, the inverse quaternion times the original vector times the normal quaternion. Okay, and remember, this is the quaternion what we are going to use. Now, how to invert the quaternion? Two things we have to do. First, these multiplications will come later. How to create a four-dimensional vector out of a three-dimensional vector? Okay, do you remember the definition of quaternion? It has a three-dimensional vector inside and a scalar. Okay, we use add 0. If we are adding 0, we are changing nothing. So, to convert a four-dimensional and three-dimensional vector in a quaternion, we keep this vector as the fet, as the bold Q, and we add 0 scalar to it. And this is our new quaternion, which represents this vector. Okay, the next thing is how to invert Q. What we say is the congruent of Q is Q star. Okay, I said before, if Q moves us from here to here, minus the inverse, the congruent Q will move us from here to here. The solution is very simple. We invert alpha, minus alpha. Okay, and then let's apply minus alpha in these positions. Then it will be the cosinus from minus alpha divided by 2 plus the vector A multiplied by sinus of alpha divided by 2. Maybe you will remember the cosinus of minus alpha is exactly the same like cosinus from alpha, so this part doesn't change. To invert this, I have two ways. I invert the angle, or I invert the vector. If I rotate with a vector in this direction, it's exactly the opposite if my vector is looking in the opposite direction. And both are the same. I can use minus A, and the rest will be the same. Or I can just say sinus from minus alpha is minus sinus from alpha. And then I have here the sinus. So in any way, it will be the same. So the congruent quaternion will be cosinus from alpha divided by 2 minus my rotation vector multiplied by the sinus of alpha divided by 2. This is. Okay, then we have already everything which we need to create this rotation. A few more words about this rotation. Let's assume this is my rotation's axis, and this is my rotation's angle, alpha. And I am rotating from here to here, my original point and my final point. And this is my coordinate system. And this vector is looking anywhere in this three-dimensional space. Okay. Now, this point, the definition of this point will be 0. Do you remember? I'm converting this to a quaternion, and then its coordinates, x, y, and z. This is its position here. Okay. The quaternion will be defined by their cosinus from half this alpha plus this vector. This is my rotation vector times sinus from alpha divided by 2. And everything here shall be normalized, so the length of n shall be 1. Else we get a mistake. Okay, and you remember then we have to implement this operation. A little bit complex, a lot of multiplications. Let's see how it works. The result will be the new vector Q, W, sorry, will be the inverse of Q, my rotation quaternion, the conversion of V to a quaternion, just adding a 0 here, and again multiply by my original quaternion. But remember, this multiplication is this operator, Clifford multiplication. We will see that later. Okay, altogether is this quaternion, do you remember? It's the original quaternion, multiplied by the position of P, which is this, do you remember? And again multiply by, here you can see, inverse quaternion. So let's do this multiplication 2 times. Do you remember we did it already once? Now we have to do it 2 times. Okay, and now how to accumulate rotations. Here, this complex way is only to rotate a vector or a point. Just to accumulate rotations, we don't need to do something like this. We just multiply the quaternions, which represents the different rotations. Okay, let's say we have these 3 rotations, A, B, and C. First A, then B, and then C. Then we multiply, do you remember, from right to left? First we multiply A times B and times C, and this will be my total quaternion. I am multiplying quaternions, and the result will be a quaternion 2. So this rotation includes these 3 rotations. And each of them shall be a length of 1. So if all of them have a length of 1, the result will have a length of 1 too. That is a nice thing here. I don't change the length of the operators, of the quaternions when multiplying. Okay, and now going backward. Do you remember we defined the inverse quaternion, the congruent quaternion? Okay, if we saw something like this, going backward is the same way, going back with the inverted rotation. So the total D will be A times B times C. The inverse will be inverse C, inverse B times inverse B times inverse A. So we are going the same way back. And this will be the rotation backward. Okay, and here is accumulating rotations, and at the end, if I'm going to rotate a vector or a point, we have to do this little bit more complex step. Okay, now let's assume the going a rotations through the 4 corners. Did I say 4 corners? No, sorry. three rotations axis, 2 corners. So we rotate in X, in Y, and then in Z. So as before, we have our inertial measurement unit, and we get the rotation speed in all these axes. Now let's try to find a quaternion which represents this rotation. First, the long way. Okay, but be aware the gyro tells us the rotation speed and not the rotation delta. So we have to create 3 rotations in 3 angles, alpha, beta, and phi. And this is the rotation. This is a 3-dimensional vector, which we get from the IMU. And this is the rotation speed. If we multiply this 3-dimensional vector multi delta t, or steps where we place the rotations, then we get the rotation in these 3 axes, for X, for Y, and Z. Then to create this rotor for X, with the angle of this, do you remember the definition of quaternion? Is the cosinus of alpha multiplied by the rotation vector. In this case, X is 1, 0, 0, multiplied by sinus. So the result quaternion will be the cosinus of half alpha, and then plus this vector, sinus from half alpha, comma, 0, comma, 0. A very similar thing when we are using this with Y. We get the cosinus of beta, which was the rotation in this axis, multiplied by the Y vector, which is 0, 1, 0. And then the result will be this. And exactly the same using the rotation phi applied to the axis Z. Something like this. This time the vector will be 0, 0, 1, and the result will be something like this. And the total quaternion of these three rotations is first the rotation of Z written to the right times the rotation in Y times the rotation on X, and this will be the total quaternion, my rotor, for this time step. Okay, and now the total attitude will be the old attitude. I'm going to call my attitude Q multiplied by the rotor. This is the rotor, and now I have my current attitude with a quaternion representation. And the original attitude will be, for example, pointing in this direction. And then I am accumulating all rotations, and then I have at the end a quaternion which tells me how did I come from this original attitude to this current attitude. And this is the representation of my current attitude, the integration of all rotations I have done from the beginning. So at the beginning I have to define this Q, in which direction I am looking. Now let's see how to use the inertial measurement unit, the IMU, in a most direct way. Here you can see we are going through corners. We don't have to go to corners. We can know the direct rotation angle. Okay, do you remember here we have our rotation speed, and it's a three-dimensional rotations vector. So it includes the rotation in this axis, the rotation on this axis, and the rotations of this axis. The one which is rotating faster will be longer than the others which are rotating slower. So we can say this V is a vector on my rotations axis, which include all three rotations. This rotation plus this rotation plus the rotation will give me this sum, the total new vector, which is exactly what I need to know around which vector to rotate. Okay, this is something I can use. Another thing I can use is the delta time. The delta time tells me how often I am reading the inertial measurement unit. And now I have everything which I need. I need the rotation axis and the rotation angle, the total rotations angle. And the rotations axis is the sum of all these three rotations values. That is V as a 3D vector, what I directly get from the IMU, but I shall normalize. That's all. I normalize this. I have a problem if I have no rotations, but this I have to check in my program. If the rotation is 0, then do nothing. Else I can normalize. Okay, and the angle which I am rotating is the absolute value or the length of all these three rotation speed multiplied by the time step, the delta time. Okay, and the new rotor will be the next slide. Okay, the new attitude will be then the old attitude multiplied by the rotor, and that is the new rotations vector. Okay, then I have three ways to do exactly the same, or almost exactly the same. The first way, going through corners, is what we saw before. So I go the vector X, the vector Y, and the vector Z, and then I multiply the total rotor, and then I multiply to get the final attitude. Now let's do the same without going through these corners. I said before, I have the rotations axis, which is the normalized rotation speed vector, which is a three-dimensional vector. I have the rotations angle, which is the length of the rotation speed multiplied by the time step. And then the new quaternion is, I'm going to call the rotor, is the quaternion of cosinus from half the angle and plus the rotations vector times the sinus of half angle. So it's much more faster than this. I have much less sinus and cosinus take much time. And I'm going the direct way and not to three corners. I'm going the direct rotations axis, much nicer. But there is another way how to improve it even better, to remove these sinus and cosinus, because sinus and cosinus costed too much time, and maybe I am controlling something which is flying very fast. For satellites, it's okay. Satellites are moving really slow, so it's not a real problem. But quadrocopters, for example, they are vibrating a lot, and then I have to consider this. Or a missile, which is flying with 3 times the speed of sound and making very agile movements, then we have to compute very fast the rotation. Then there is a very nice approximation. This is the approximation of Mr. Rodriguez and Mr. Antoni Grau. It's very difficult mathematics. I have tried to understand how it works. I'm sorry to say this, I do not understand how it works. But we have tried it in many simulations. We have tried it in satellites, and we have tried it in the drones, quadrocopters, and it works. It works properly. Even if we don't understand how it works, but it does almost the same like the exact mathematics we saw before. Almost the same, but the difference is really minimal. And the nice thing is they are not using any cosinus or sinus. They are using very few operations. Therefore, it's really, really fast. What they do is, we have the Q. Do you remember the Q is the encoding of my last attitude? At the beginning it was maybe like this, and I am integrating all rotations, and my current attitude could be, for example, something like this. Okay, this will be my Q. The vector representing my current attitude, and that's at the same time is the Quaternion which moves this initial attitude to the current attitude. That is Q. Okay, what they do is they take half Q and multiply by the rotations speed, a three-dimensional vector, plus 0 is a Quaternion times delta t. Okay, and the new attitude is the old attitude plus the rotor, which we compute here. I said before, I don't understand how it works, but it works. And it has very few operations and no sinus and cosinus, and therefore it's really, really fast. Okay, these are the three ways which we use. Most of the time I prefer this because I understand this, and it's going the direct way without these corners I said before. Okay, and now let's talk about this operator, the multiplication operator. You can see we have these multiplication operators all around, and we didn't define it. Now we have to define this. Okay, what is this operations operator of two quaternions? And this is the result. Very difficult to remember. If I shall read it, okay, this is the scalar part, and that is the vector part multiplied by three orthogonal imaginary numbers. Who shall remember this? But there is a better way to do exactly the same. We don't need to remember this. Do you remember we mentioned how to multiply binomes, and this is what we are going to use now. But first, let me show the different operators for quaternions. The sum of quaternions, the quaternion Q plus the quaternion R, is just this quaternion plus this quaternion. Do you remember the definition of quaternion? I can just add both scalars, and I can just add both vectors. So it will be the sum of both scalars plus the sum of both vectors. And do not try to add this plus this, because this is an scalar and this is a vector. You cannot merge them together. Okay. The inverse of a quaternion is, do you remember, we use invert the vector part of the quaternion. The length of the quaternion is the root of the sum of the squares of its four elements. And normalizing a quaternion is the original quaternion divided by its length. And therefore it is a problem if you initialize with 0, because if you initialize with 0, then the length will be 0, and then you will be dividing by 0, and this will be an error, numerical error. And now the most difficult part, the multiplication. Okay, we have the two quaternions, Q and R, and then we are going to multiply this plus this. And do you remember, as I said before, let's do it exactly like multiplying binomes. And let's say we have a binom A plus B multiplied by the binom C plus D. Plus these are bold written because they are vectors. So let's consider this. We are multiplying a sum of a scalar plus a vector. Okay, the result will be, do you remember, A times C plus A times D plus B times C plus B times D. And this is going to be an scalar. Here you are multiplying an scalar with a vector, the result is a vector. Here again, the result is a vector, and here we have the question. We are multiplying two vectors. The result can be an scalar or can be a vector. But there is something more. These are not only vector, these are imaginary values. And therefore, we have to consider something more. This is the multiplication of this imaginary value times this imaginary value. And do you remember what is the result if you multiply two imaginary values, e times e or e times j? J is another imaginary value. Then the result is minus a real number. Okay, then the result will be, we have to change here from plus to minus. Okay, now we have another question. All of these are clear. Multiplication of two scalars, multiplication of a scalar and vector, again a scalar and vector, but here the multiplication of a vector times a vector. And for this, we have two options. We have the scalar product and we have the vector product. And we are going to use both of them. So, for this multiplication, we are going to get an scalar part and a vector part. And one of them will be minus, because they are imaginary values. Okay, then the result of this is what we saw before. This is exactly the same what we saw here, only I have here with A, B, C, and D. But here we have exactly the same with the Q and R. Okay, nothing new. But now the next step is to separate what is scalar and what is vector. We can see this is an scalar, and the rest is a vector, with the exception of the scalar product of this. Okay, then we make the separation between the scalar part and the vector part. And the result of this multiplication shall be a quaternion 2. And do you remember the quaternion had these two parts, a 3D vector and a scalar part. So if it works, the result shall be the same. It shall be corresponding to this. And this is the scalar part minus the scalar product of these two, and minus because they are imaginary. And the vector part of the new quaternion will be this multiplication plus this multiplication plus the vector product of the multiplication of these two vectors. Okay, and that is something you can remember. This is nothing more than multiplying a binom, which is more simple than trying to remember this. Well, of course, if you are just writing the program, you can just type this down and then you can forget where this complex number comes. Just multiplying this and the program will execute. But if you want to remember how it works, it's better if you remember this way, like example, multiplying binoms. And the next part, we have already rotations using matrix, rotations using quaternions, and now let's see Euler Angle. I said before, do not use Euler Angle for computations. Use to read the current rotations, very small steps, and to make the representation, for example, for the pilot. For the attitude indicator, which is called to the artificial horizon, only for that we are going to use the Euler Angles. But there is something very special with Euler Angles. We were talking always about rotation in Z, in Y, and X, but there are many other ways to represent rotations. We need 3 parameters, but not only D. We can have 12 different representations of any rotations. What we are using is this standard, which is the standard roll pitch yaw for aeronautics, which is the same which we are using for satellites. But all other, if you want to do some numerical exercises, can be the same. Let's take, for example, this. How can you represent any rotation if you are not touching, for example, the Z vector? Look, here you're rotating X, here you're rotating Y, and you're rotating X. And you say with this you can represent any rotations, including rotations on Z. How can we do that? I'm going to show this. And this is something similar with all other. With some of this. Here we have the same case, and here we have the same case, and so on. Okay, but let's take only the first example. Sorry. It doesn't matter. Let's take only the first example. In this example, I want to rotate it Z, but without touching Z. Let's take this example. This is Z, the blue one, and I would like to rotate from here to here. That is obviously a rotation around Z, but I am not allowed to touch this. What I can do is, according to this, first X, then Y, and then X again. This is X. I am rotating in X. Remember, I want to go from here to here. Remember this. Okay. Then I'm rotating in X. I am rotating in Y, and I am rotating in X again. Did you see? I got from here to here without touching this. So it was possible to make any three-dimensional rotations touching only two different axes. It makes everything more complex, and it works because after every rotation the axis change, then you have a new the new definitions of axis. That is something we have to use if some rotation parts in a satellite fails. Normally we have satellite devices to rotate on this axis, on this axis, on this axis, and to make any rotations we use add these three vectors. But sometimes, for example, if the device to rotate in this axis has failed, then we have to make something like this to reach any rotation angle we need without having to use this device. Well, but this makes everything much more complex. But just to remember, it's possible. Okay, and this is what we are using for yaw, pitch, and row. This is the standard. This is the sequence of rotation in first in Z, then in Y, and then in X. Okay, and just to show, for all of these combinations of axes, you can create a rotations matrix. For these 12 combinations, let's go a few slices back. Here we have combinations. Let's take any, this one, and let's try to create the rotations matrix for this. Here I have this, and I have a rotation in this angle, in this angle, in this axis, in this axis, and this axis. And here is something special. I am writing here an apostrophe because after this rotation, this set is not the same like this. Now it has another attitude. Okay, do you remember that is the rotations matrix for Z? That is the rotations matrix for X, and this is again the rotations matrix for Z. So I have encoded these three rotations in these three rotations matrix. Now I multiply these three matrices, I get the total rotation, this big matrix, which represent this rotation of these three axes. So if you would like to do some mathematics, you can spend a lot of time finding how to make rotations using don't touching one of the axes. Okay, and this is what we are doing now for rotations. Just a second, please. Here. Okay. Now we conclude the chapter of rotations. I hope you enjoyed it, and I hope you understand much better about rotations. Okay, thank you very much, and see you.